Hey everyone, welcome to another video. In this video, I'm going to show you how you can speed up the SuperAnimal top view mouse model, specifically the HRNet 32 version. And I'm going to link this one with YOLO detection model. So YOLO is going to provide the localization and then cropping to the DeepLabCut HRNet, and then HRNet is going to provide us with pose estimation. And I'm going to show you how you can do this and make your DeepLabCut pipeline specifically with the HRNet 32, how you can make that a real-time inference module. So without further ado, the repo that I'm going to be showcasing is here under my GitHub. It is currently a private repo, but by the time this video comes out, I should have had this made public. But if by that time it's not public, please leave me a comment and let me know. So I'm going to be using this walkthrough. This is a technical demo. Okay, so just bear that in mind that this is a technical demonstration. Things I'm about to show you are in a technical way possible to do for yourself. There is a little bit of a learning curve with this. I've had to do some C++ custom coding for this project to be made to be able to make it real time. So I'm gonna open up my Anaconda prompt here on the left. But before I do that, let's go ahead and take a look at this video I generated for this demo. So I'm slowing this down. I'm gonna play this one of these videos side by side videos. One of them comes from the original floating point 32-bit precision model. And the pose estimator in this case is the HRNet W32. But we'll go through this workflow and I'll show you how you can install the repo for yourself. And I have everything that you would need in the README file here. Okay, so one more time that this is a technical demonstration. The DeepLabCut and the YOLO models that I'm about to use. If you're going to use your own YOLO model and DeepLabCut model, please read their license agreements because both of them have a little bit of a different caveats for use case. The SuperAnimal DeepLabCut models are under MIT license, whereas YOLO models are not. So I'm navigating over to where I have my preview repo. And then from here, I'm going to create a new Anaconda environment. So create an, let's call this demo, and I will install Python 3.11. So my demo environment is going to be fresh, and I will be installing whatever I need inside of that. Meanwhile, I am going to go to PyTorch and pull one of the PyTorch installations here and use that. It's a fairly simple and standard stuff. So I've created a new environment called demo and then activated it. There we go. So this version of the PyTorch is going to get installed, and after this I want to check whether my CUDA is being detected. So I'll go ahead and pause my OBS at this point, and then I'll come back after that. Okay, so the PyTorch is installed. Let's go ahead and check it. So I have these commands here available for everyone to use under the README. So in my case, the CUDA availability is true, and then Torch version is the one that I just installed. So that is good to go. Let's go ahead and install the GPU version by using this command here. Okay, so again, this is going to get installed. I'm going to go ahead and wait for this to be finished. There's also this CPU version if you're going to be on a laptop, and also the AMD profile for anybody who's interested in using an AMD GPU. If you are going to be using an Intel GPU, then there's a profile for you as well. Okay, perfect. So everything is installed here for running the GPU profile, and I have to make sure that I have the NVIDIA CUDA runtimes for the GPU, the CUDA version that's installed for me, and it's going to work. The other thing I want to make sure is that TensorRT for NVIDIA got installed. So I'm going to do pip show TensorRT. Okay, this looks good, and this is compatible with what I have. Good. So now that I have the Max DLC installed, I'm going to go ahead and launch the graphic user interface, and that is the command for that. And here we go. So the project is a technical demo. It's a preview. This is just to show you what type of inference speed you can get out of uh, decreasing the latency and optimizing the key point estimation models. So I'm going to go ahead and go through this entire section of this demo, but please make sure to read over both the in-depth walkthrough under the docs here. There is a detailed walkthrough that will guide you through everything basically, right, including the command lines, and you can see where the artifacts are being saved. Okay, so that's available for anybody who wants to use command line interface. I'm going to first create a project. Let's call this one test demo. And then it's going to ask me where I want to save it. I will delete this old one and create a new folder, test DLC max, and then save that one over here. So once you create a project, it's going to tab you over to the next tab. And in the next tab, we need a video. This is the video that I was showing you initially, and I need a model, the YOLO model. I'm going to use a previously pose estimation model. I was working on behavior scope X, which utilizes a single key point estimation checkpoint to extract key points as well as visual features from the frames to be able to then train a behavior classifier. So from that project, I'm porting over this YOLO 26 and pose model. This model can provide me with bounding boxes as well as key points, but in this project, I'm only going to use the bounding boxes. And then for the HRNet, this is the fine-tuned the snapshot. For detection subjects, there are going to be two subjects, and the YOLO source is going to be detection only. And I will leave everything else the same. I turned the detection precision to FP32. Here we can type in whatever the names are for the body parts. The biological landmarks shorthanded like that. I will leave these paths as they are and then move over to the optimization tab. I will be doing TensorRT and Onyx optimization. And if you are on a CPU, please use the portable Onyx only. So I'm going to show here with the Onyx and TensorRT FPS. So then this is going to give me here the typical batch size is going to be 2 because of the way that the Mars videos are. There are at least typical number of mice 2, and then also the maximum batch is also going to be 2 because there are only 2 animals and 2 crops to be had from those animals. Okay, so with those set, I can run this optimization. It's going to load up DeepLabCut and then the TensorRT to then do the optimization. So I will go ahead and pause OBS here. This can take anywhere from 5 to 15 minutes. So we'll wait on this. Okay, so the optimization finished, and let's take a look at this. So down here on where the terminal outputs are rendered, you can see the batch 1 and batch 2 profiles. So for the PyTorch version itself, the inference cost was 25 milliseconds for batch 1. Then for TensorRT, that batch inference dropped to 3 milliseconds, 3.067 milliseconds. So that's a speed up of 8.197. That's crazy. But for batch size of 2, it's even faster. None of this actually matters if the biological measurement itself is bad. So for sake of making sure that the measurement, the source of the error or deviation from the FP32 key point placement is not compromised, I'm going to go ahead and run a validation on the step number 2 here, which is going to run both models, the FP32 and the newer version of FP16. Now I'm expecting it not to match because certain landmarks, specifically the peripheral landmarks, they tend to deviate a lot after quantization happens. So here, for example, take a look at this. So I have a maximum pixel distance now 35.715 pixel difference. But overall, in terms of the average pixel error, 0.064 between the FP32 and FP16, the cosine similarity score of 0.99. Not a bad outcome overall, but for certain landmarks, this biological parity is going to fail. You're not going to get the similar results as the FP32. Obviously, that makes sense. But if you're not relying on peripheral only landmarks and your landmarks or your video quality is high enough, but the biological parity in that case could be preserved. But for visible key point errors, 0.064 pixels on average, that is not bad. I would use this model. So on the next tab, I'm going to go ahead and run a live demo. And I'm going to switch these numbers down a little bit. So this is going to run the fastest TensorRT model. And let's go ahead and do a no-show analysis first. So we get the pipeline throughput. So this is going to be the full throughput. This includes the YOLO detections and then the key point estimation. And on the bottom here, we have these numbers to kind of now go off of. So here, the pipeline throughput was 64.42 FPS, with YOLO detections taking up approximately 9.92 milliseconds per frame. And DeepLabCut, the HRNet pose estimation time went down significantly with 3.70 milliseconds. And we can compare this one to the reference PyTorch model. Let's go ahead and wait for this one. So remember, this one with the optimized model, we're getting 3.7 milliseconds for the DLC inference speed. So now the FP32 uh, version of the model is almost done running. And here we go. So DLC DeepLabCut pose estimation milliseconds 26. So 3 versus approximately 3.5 versus 26 milliseconds. Uh, I don't know how much that would affect anybody, but in my case, if I were to do this apply this DeepLabCut model for real-time inference and real-time feedback on anything animal ethology related, I would want the lower latency model to be used for deployment personally. And then the pipeline throughput went down from 60 all the way down to 26. So I'm going to stick with this one, but on the live preview, we can take a look at what we get. Because if it doesn't work for the live preview, like there's no point in me optimizing these models, because my whole goal was to get the pipeline to be as fast as it can be so that I can do live feedback, kind of haptic feedback or something else for the animals as well. Okay, so here's the steady state, 70 FPS. In terms of the what this is doing for the, how much space it's taking up on my GPU, both YOLO models, the YOLO model and the DeepLabCut models both don't take up a lot of space. So if I rerun this, you can sort of see here, I was at 1.2 and now I'm at like 1.5 and 1.3. So incredibly efficient models to run on GPU after you have optimized them. So here between the two runs, we're getting approximately 69 FPS throughput. So now I'm going to go ahead and benchmark this by utilizing a larger number of frames. I'm going to set this one to be 900 frames. We'll get a nice benchmark graph over here for the live preview versus headless versus the FP32 versus the FP16. And we can then compare what I'm getting on this hardware that I'm using for demo purposes. So I will go ahead and run this, and I'll stop the OBS for now and wait for this to be done. Okay, so the benchmarking is done. I have over here on the right, you can see the FP32 headless gives us about 28.3. FP32 live with the preview on actually does a little bit better, but nothing significantly different. The FP16 headless gives us 62, sorry, reading it backwards, 62 FPS, and then the FP16 with the preview on gives us 66. Not a bad outcome, right? So at least 2x difference between the original DeepLabCut HRNet 32, the super animal model, and then the more optimized version with live preview with some custom C++ coding for optimization. So this is something that you can try on your own hardware, see if this can be useful for you. I'm not going to guarantee that this is going to work for everybody, but in my case, it's working really well. So I'm going to put this repo out, see if other people can use it too. And then if you do these benchmarks and you want to utilize them later for anything, obviously there's a way that you can export your entirety of the outputs, the all of the benchmark JSONs for individual models. You can export as a zip file. So that's it for this video. I hope this was helpful. Uh, yeah, so let me know your thoughts and your comments down below. I love to read on those and to learn from anybody who wants to teach me anything. So thank you so much. See you in the next video. Bye bye.